welcome everybody. I'm just writing down the two statements. So I wrote down the theorem, which we're going to prove in a second, and I'm writing down the lemma that we will need in this proof. So let me just do that. So if you remember, we looked at the shape of these sort of ideals, I divided by x. And that's what we had. And finally, if x is not in P, then Ix is I. Okay, good. So we were looking at primary decompositions, and where we ended up last time is we have an ideal which is decomposable, so it admits a primary decomposition, which is not automatic. We built a minimal primary decomposition for it using these ideals Ji. So that means that the radicals of the Ji's are some primes. The primes are different for every I, and none of these Ji's is redundant. Yeah? So we have such a primary decomposition. The Pi denotes the radical of Ji, and then we are looking at these two sets. One of them is the set of the primes that appeared, and the other one is the set of all prime ideals among such ideals. The point being that the first guy depends a priori on the decomposition, and the second one does not. That's the point of this theorem. Okay, so let's prove it. So I'm proving the theorem. Okay, so let x be an R. What we're going to do is we're going to look at this ideal I divided by x and analyze it. So the first thing you want to do is, well, this is a finite intersection, and you can pull the intersection out. Okay, this requires a check, but I'm not going to do it. It's all these guys that multiplied by x belong to I. If multiplied by x you belong to an intersection, then multiplied by x you belong to every of the Ji's, and you can also reverse the containment. Okay, so this is not deep, it's a check. And now we're going to take radicals. So again, if you take a radical of a finite intersection, you can push it through. So we are doing this, okay? Okay, but now we have these radicals, and we have them up there. So if x is not in I, then this radical, also if x is not in Ji, let's think about it. So if x is not in Ji, then I'm going to see the Pi, okay? So if x is not in Ji, so it's all the i's such that. So I certainly have that. What if x is in Ji? If x is in Ji, then this ideal Ji divided by x is the whole of R. So the radical is also the whole of R. When I take in an intersection, I don't care about R, right? So the guys which the ideals which contained x don't contribute, and the ideals which did not contain x contribute the prime. Okay, so this is just a computation from lemma 6.6. Okay, very good. So now suppose that the radical, sorry, did I write it correctly? Yeah, of course I forgot the radical here, sorry. Now it makes more sense. It's the radicals here. So suppose the radical of Ix is prime. Okay. Well then, we know that, so this is a prime ideal, and we wrote it as an intersection of prime ideals. If you remember the very beginning of last lecture, if you have a prime sitting in the intersection of primes, then it actually sits in one of them, right? And also there was this kind of furthermore, which showed you that if a prime is equal to an intersection, then the prime is one of the primes here. So that means that this radical being prime is equal to some Pi0 for some I0. So that means that all the prime ideals of this form show up in our intersection, okay? Vice versa. So this is using proposition 6.1. very beginning of last lecture. Now the other direction. Now for every I0, what do we have? There exists an x in R such that x is not in J I0 and x is in J I for I not equal to I0. Okay, why is that? This follows from the fact that our decomposition is minimal. We haven't used it yet. Okay, if for everything which sits inside all of the Ji's without I0, I also have to be in J I0, that would mean that I could get rid of J I0 and get a shorter decomposition. Yeah. If you remember, minimality had two things. Every prime appears once, and nothing is redundant. This is using the non-redundant condition. Okay, so because it's minimal, we have that. Okay, but that's good news, because now for such an x, for this x, what we have is the radical of Ix is exactly this. Okay, so if this guy is prime, then it appears, and every one of the things that appears for every I0, I can see it as the radical of this form. Okay, so that's the proof. So that's good news. Okay, so now a bunch of some vocabulary related to ideals, primary ideals and decompositions. Okay, so the prime ideals Pi in the theorem are called associated to I. Okay, you should think, collection of primes dividing your number. That's what's happening here. Okay, and now what would happen if you so if you take all of these prime ideals, by the way, and you intersect them, so this is something you have to check, then you get the radical of I. Okay, the radical of I is the intersection of all the prime ideals that I is contained in, and then you check that this is actually exactly those. Okay, so the intersection of all these is precisely the radical of I. Okay, this is a check. Okay, now if you imagine that you had a radical ideal, so an ideal which is equal to its own radical, when you do the primary decomposition, you will see that the j's that show up are actually already primes. Yeah, so you can pass to the underlying primes. So that means that if you have a radical ideal, then you can find a primary decomposition made of primes. Okay, so that's true for a radical ideal. Moreover, these primes are then unique because the primes are exactly the primes that appear in the statement of the theorem. Okay, so if you take a radical ideal and you look at primary decompositions by primes, it's essentially unique up to reshuffling. Yeah. Now you could ask what happens if you take a primary decomposition of a radical ideal that is not necessarily made by primes, and it turns out that in that case the primary ideas will necessarily be primes, but we are not going to prove it. Okay, this is in Atiyah MacDonald, and there is a remark in the lecture notes which tells you where to look for it. Yeah, if you are curious. Okay, very good. So now we are actually going to do something. Let's see. So this was remark 6.9, and now example 6.10. So you might not be used to this in this lecture because we so far follow the Bourbaki tradition and we do no examples, but now we're actually going to do an example. Okay, so first an easy example. So suppose that we have a number n which is equal to a product of primes p1 n1 times blah 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 times pk nk in z, pi distinct primes. Okay, what happens in this case? Well, I mean, nothing surprising. If you take the principal ideal generated by n, so all the elements, all the numbers divisible by n, then you see, well, quite quickly that this is, in fact, the intersection of such ideals. And then this is actually a primary decomposition. And the associated primes are the PIs. Okay, so nothing particularly crazy happens in this case. Right. Okay, let's look at a more interesting example. So now consider the following ideal. We're going to generate it by two elements, x squared and xy, and it's going to sit inside the ring of complex polynomials in two commuting variables, x and y. Okay, so that's not a principal ideal. And let's see what happens. So the claim is that x squared xy is equal to the intersection of the ideal generated by x and the one generated by x and y squared, and this is a primary decomposition. Okay, so let's try to work it out. So there are things to check. First of all, we have to check that this equality holds. Okay, so let's do that. So if we have some polynomial p inside here, what does it mean? Well, it means that we can write p as x squared q plus xy r for some polynomials. Sorry, cxy. Okay. So, well, both of them are divisible by x, so it's clearly it's in here. And what about the second one? So this guy consists of polynomials that are products of polynomials which have so the degree, the combined degree of x's and y's has to be at least 2, right? That's the point. So the combined degree here is x squared, so it's 2. So x squared belongs to x comma y squared, and xy does as well. So this is actually kind of obvious. Okay, since these guys do. Okay, vice versa. Now suppose that p of x, y, lies in the intersection. Well, so that means that p in here is equal to x squared times some q. Okay, let me call it q0 plus xy q1 plus y squared q2. Okay, what is divisible by x? Well, this is divisible by x, this is divisible by x, and this is divisible by x. So we conclude that y squared q2 also lies in this ideal. So this guy must lie in this ideal. Okay, but that means that, where are we? This certainly lies in the ideal generated by x squared, this lies in the ideal generated by xy, and this lies in the ideal generated by xy, because x divides this, right? So let's write it. So we can write, So we write Q2 xy as Q2 prime xy times x, and now clearly P of x belongs to the ideal generated by x squared and xy. Okay, so we proved that the conclusion is, let's write it down, that this ideal is equal to this ideal. Now we need to check that these ideals are primary. Okay? So let's do that. So Cxy divided by the ideal generated by x is just Cy, which is a domain. Conclusion, this is a prime ideal. Okay? Now what about the other ideal? So if we take Cxy and divide it by the polynomial generated by x and y, so not quite this thing, okay, then we are getting C, a field. If we are dividing a ring by a polynomial and we get a field, we know that the polynomial is, if we divide the ring by an ideal and we get a field, then we know the ideal is maximal, okay? So this is maximal. And if you remember what we proved last week, powers of maximal ideals are primary. So xy squared is primary. Actually, it's more than just primary. It is xy primary. So this ideal is prime, so it is primary over itself. This guy is primary over xy. Okay, so that's good. The one last thing we need to check for the, well, so this is a primary decomposition. Okay, we didn't check its minimal, but it is. Okay, so but this is a primary decomposition. Okay, we can check that it's minimal. For minimality, you just need to see that neither of them is contained in the other, which is obvious. Okay, so okay. It is easy to see that this is a minimal primary decomposition. Okay? Okay, very good. Okay, so now we need to introduce some more language, and before that we are going to have one more lemma, doing time-wise. Good. So here's lemma 611. Okay, so let I be a decomposable ideal, and we are going to introduce two sets. So let S be the set of prime ideals associated to I. Okay, so these are the primes that appear as radicals of the ji's in some minimal decomposition. And then let I, this is curly I, be the set of prime ideals containing I. Okay, both are ordered by inclusion, so that's clear. And now here's the statement. The minimal, the sets of minimal elements of S and I coincide. They have the same minimal elements. Okay, that's the statement. Okay, so let's prove it. So here is proof of lemma 611. Okay, so by theorem 6.8, which we proved today, the radical of I is equal to all the primes that appear in S. Okay, remember? I is the intersection of the ideals. When we pass to radicals, the intersection is finite. We can pull the radical through the intersection. The radicals of the J's in primary decompositions are exactly these P's in S. That's exactly the associated primes. That's just the definition. So we have that. Okay, and moreover, because of now what happens if you have two primes in here in this intersection and one sits on top of the other? When I take the intersection, I don't need the bigger one. I only need the smaller one. So I can straight away change it to S min here, where S min is the set of minima of S. Okay, and we also define I min analogously. Okay, so the radical of I is the intersection of the P's in S min. Okay, so now we are starting with the proof properly. So let's take some P0 in S min. We need to show that it is in I, well, in I min. That's what we need to show. Okay, and suppose that it's not in I min. Okay, suppose not in I min. Okay, so it's not in I min. It certainly is, it sits in this intersection here. So the radical of I is inside of it, so I is inside of it as well. Okay, so note that I sits inside here, but it's not in I min, so that means that there exists some other prime. Let me just check notation. Prime P prime 0, which has I inside, so it lies in I, but it's a minimal guy in there, so it lies properly inside P0. Yeah, I'm not the minimal guy in I, so there's something in I which is smaller than me. Okay, so that's good. Okay, so what does that mean? Well, it means that the intersection, let me say, I'm getting confused now. Right, so now I want to claim that, so I need, right. Okay, so so this is what we do. This is I, it sits inside here. I can take radicals. The radical of a prime is the prime itself, but this is the intersection of the primes in S min by what we have above. And we proved at the very beginning of last lecture, this is proposition 6.1, that if you have an intersection of primes sitting inside the prime, that one of the primes has to sit there. So there must exist a P in S min such that P sits inside P prime 0. Okay, but that means that P sits inside P prime 0, which sits inside properly P0. Okay, so this is not, this guy comes from S, and this guy comes from S, so it cannot be in S min. Okay, that's a contradiction. Oh, okay, so if we start with something in S min, we produce something in I which is smaller, then we get to produce something in S which is smaller, and that's how we conclude. Okay, so that's one direction. So this shows that S min sits inside I min. Now the other direction, let P sit inside I min. So this means, again, that I sits inside P. We can take radicals. Of course, on the other side, I don't need to take the radical. And this is, again, the intersection of all the primes, let's say P prime, in S min. So again, there is a P prime in S min such that P prime is inside here. But now, if you're in S min by the intersection, we see that we have that. Okay? So now P is a minimal guy, so that means that P prime is in I. P prime is smaller equal, well, it's contained, but not properly in P. P is in I min. So P prime is P. So I min sits inside S min. And we're done. Okay? So these two minima coincide. Okay. So now terminology, the elements of S min are the isolated or minimal ideals associated to I. Okay, so right. And the others so S take away S min are called embedded. Okay, the terminology comes from algebraic geometry, so I won't be able to tell you much about where it comes from, but that's what it is. Okay, but these are the names: minimal isolated for the guys which are in S min, and embedded for the guys which are not. Okay, so in the second example of is 6.10, so just above here, let's look at it. What were the associated primes? So the primary ideas were x and the square of xy. The underlying primes were x and xy, but of course one of them sits in the other. So there's only one minimal prime, which is the one generated by x. Yeah. So we had a primary decomposition. We showed it was minimal. We know what the associated primes are. One of them is isolated. The other one is embedded. Yeah. Does it make sense? Some confusion. Okay. I know there's a lot of terminology. Okay, now if you go back to what I was mentioning before, if you start with a radical ideal and you take a primary decomposition by primes, and in fact every primary decomposition is by primes, then you immediately see that each of the primes is minimal. Because if you had a prime in the primary decomposition which was not minimal, you would get rid of it because it wouldn't form part of a minimal primary decomposition. Yeah, think about it. It's a bit different with primary ideals, different with primes. Okay. Anyway, so that's where we are. Next lemma. So lemma 6.12. R is a ring, I is an ideal. Ring R. Okay, we are not assuming that I is decomposable here, by the way. So there exist prime ideals that are minimal among what? Among all the prime ideals containing I. what am I saying here? I'm saying here that the set I min that we looked at in the previous lemma is non-empty for every I without the assumption that I is decomposable. Okay? How do you see this? Well, it's an exercise, but you've essentially done it. Exercise. See the last question on sheet 1. Okay, it's an exercise in Zorn's lemma that there is the smallest prime ideal. Okay, just do that. Okay. Right. Right. So for once we are ahead of schedule, so we can start the next topic. Okay, so this is it on primary decompositions. And now we are moving to the next thing. So this is section 7. We're going to talk about noetherian rings. This is very important. Noetherian rings are essentially the class of rings we want to study and we want to understand. I will give you the definition in a second, just about the name. So it comes from Emmy Noether, very interesting and important mathematician. So about pronunciation, I mean, my German is not perfect, but the point is that the H is really silent, so it's not a th, it's a t, and this is like a single vowel. Okay, so the name is Noether. So I guess noetherian is the closest English version of it. Okay, you can pronounce it whatever way you want, but I would say noetherian is somehow the way. Okay, so noetherian rings. What are they? Here's the definition. So a ring R is noetherian if every ideal in R is finitely generated. Okay. Yes, I write it with lowercase letter, which might not be to everybody's taste, but as they say, the highest honor in mathematics is when your name becomes a lowercase adjective. So, okay. Anyway, so it turns out this is a very useful and very special property. It's special, but at the same time, the sort of rings that we actually care about, they all have it. Okay, so it makes sense to think about it. So what are the examples? So first of all, fields. Why is that? So they are finitely generated, as R modules, right? Fields only have two ideals, the zero ideal and the whole thing. Each of them is obviously finitely generated. Yeah, one by 0, the other by 1. So that's not a very interesting example. More interestingly, all principal ideal domains. Okay, so this is something that you should check. It's not hard. So in particular, we have Z, we have the complex numbers, and we have all rings of the form Kx, where K is a field. Okay, so these are the primary rings these are the rings that we are particularly interested in. We want to have a theory that is as general as possible, but really what we care about is Z and polynomial rings over fields. Yeah, these are the two kind of classes of rings that we really care about. Yeah. Okay, so blah, 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 blah. Okay, first lemma. So the definition I gave you of noetherianity is not the usual definition. We are going to do a lemma which will give you the usual definition and show it's the same as the one I gave. So the one I gave is easier to state, but this is the real definition. Okay, so the ring R is noetherian if and only if whenever we have a sequence of ideals, I1, I2, blah, 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 is a chain of ideals of R there exists some k, natural number, such that for all I, we have, okay, so what I'm going to write is that this chain stabilizes. So from some point on, which is what this k is, let's just write it in terms of quantifiers. From some point on, nothing changes. So ik is going to be the same as ik plus I for every I, and in fact, this is going to be exactly the same as, sorry, the union of all of them. Let's say T. Okay, so if you take any growing chain of ideals, it will stabilize. That's the real definition of noetherianity. The property of being noetherian shows up in other contexts, not just in ring theory, and it's always a condition about ascending chains stabilizing. Yeah, that's the real thing. There's also a condition about descending chains stabilizing. That's called Artinian, but we are not going to really talk about it much. Okay, noetherian. So let's prove it. Okay, so we have two implications to prove. Let's do this one first. This one says if we are noetherian in the sense of the definition on that board, then we have this property. So consider, well, take a chain of ideals. Ideals, let well, the ideal union of all of those. Okay, so you have to check that this is really an ideal, but this is easy. So the ideal this is finitely generated since we are noetherian, right? Since R is noetherian. Okay, so what does this mean? Well, it means that there exists a collection of elements, x1 up to xn, in I, such that, let's call it capital I, such that I is equal to these guys, well, whatever they generate. Yeah, it's just definition of being finitely generated as an ideal, as a module. Okay, but now each of them has to appear somewhere. It's a union, right? So for every I at most n, there exists ji such that xi appears in ij. So now we just take max. Take j max to be the max of ji's. Okay, so now x1 up to xn, they all lie in ij max. J max. So I sits inside ij max. But of course, this is a union of a chain that grows, so this is here. So they are equal. So ij max is the k that we wanted. Yeah, so that was one direction. The other direction, now we have this condition on ascending chains, and we want to prove noetherianity. So let I be an ideal, and suppose it's not finitely generated. Okay, so we're going to construct a sequence of elements. So we take some x1 in I. Now, assuming, so this is an inductive procedure. By an inductive procedure, if x1 up to xk in I is chosen, pick xi plus 1, which is in I, but not in the ideal generated by the previous guys, which has to be non-empty because otherwise I would be finitely generated. Okay, so I take an element, I generate a submodule or a subideal. I take an element which is not in it, I generate, and I keep going. I is not finitely generated, so this procedure continues forever. So now let I be the ideal generated by x1 up to xi, we clearly see that we have I1 inside, well, they're properly inside actually. I2 properly inside, I3 properly blah, 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 blah. Okay? So these are proper inclusions, so this cannot stabilize. Okay, cannot stabilize. So if there is an ideal which is not finitely generated, then we can produce a chain of ideals which doesn't stabilize. Yeah, these are proper inclusions. This is how you see it doesn't stabilize. Yeah, everybody happy with that? Okay, so that was that. Lemma 7.2. Okay, so noetherian rings have many good properties, and one of them is that they behave extremely well under standard constructions. Okay, so if R is noetherian, and I is any ideal, then the ring, the quotient ring R divided by I is noetherian. Okay, proof. Okay, so let Q be the quotient map. Be the quotient map. And let J be an ideal in the quotient ring. Then Q take away J, Q preimage J is an ideal of R. Okay. If we take this guy and multiply it by something in R, we can push the situation by Q, and then we are still in J, and then we're in the preimage. Yeah, so this is easy. I mean, we've done this check multiple times by now. It's an ideal of R. So it is finitely generated. So we have Q preimage of J is an ideal generated by some x's. And now we push by Q. Okay, check this. And that's the end. Yeah, extremely easy. Start with an ideal in the quotient, pull it back, it's finitely generated. Finite generation is a property that descends to quotients, obviously, somehow. Yeah. Okay, so that's that. One more property. We have 5 minutes, so we can do one more. And so, okay, so I said noetherian rings are stable under standard constructions. We went through one standard construction, quotient rings. What's the next one? Well, it's localizations. So R is noetherian. S is a multiplicative. Oh, no, it's just S. I think it's just going S. Is a multiplicative subset. The localization R localized at S is noetherian. Okay, proof. Okay, so let lambda be the localization map. So if you remember, 1 goes to 1 over 1, or let's say R goes to R over 1, be the localization map. Okay. So if you go back to the proof of lemma 5.6. So let me remind you what that was. So it was this long proof where we were looking at ideals of localization and ideals in the original ring which intersect the set S trivially. If you remember, that took us half of a lecture. It was a long thing. And we were showing that there's a one-to-one correspondence between ideals in here and those prime ideals in here and prime ideals here which do not intersect S. Yeah? And in part of this, well, one of the things we proved there was that, well, how does this correspondence work? We proved that we saw that if I is an ideal in the localization, then I is equal to, okay, the ideal generated by what? We can take lambda inverse I, then apply lambda to this, and then generate. Yeah. So we take an ideal in the localization. Lambda inverse is pretty much intersecting the ideal with R. So looking at the elements in the ideal which have trivial denominators. So formally we pull it back to R, we push it, and then we generate. So the point is that every element in I comes from something in I which had trivial denominator multiplied by 1 over the denominator. That's the point. Okay, that's what it says. Okay, so I is equal to this guy, but now we are done because this guy is an ideal of R. So it is finitely generated. And hence, so is I. We take the finite generating set of this ideal as an R ideal, we push it in, and we use it as a generating set over Rs. Okay, so there's a check here, but it's easy. Okay, so check this. And that's it. Okay. Well, we don't have time to do one more. And that was quite a lot, so maybe we will just stop here. Okay, thank you.